This is the second part of our discussion on the continuous property of complex valued function. Now in this part, we are going to see the consequences of the definition of continuity. Okay, so we will observe some properties of continuous functions as well. Now let's recall the definition of continuity. So a complex valued function is continuous at a point z0 if the limiting value exists, the functional value exists, and both values are equal. So that was the first definition. We also described the continuity using the epsilon delta definition as well. So this definition says that for every epsilon there must exist a delta such that the distance between functional values and f of z0 is as small as we want, or in other words is less than epsilon whenever the distance between z minus z0 is less than delta. So in other words, we can say that small changes around z0 gives us small changes around f of z0. So small changes in the independent quantity gives us small changes in the dependent quantity, or f of z. So that's basically the main spirit of the concept of continuity. Now let's start with the first observation. So it says that if we have a function given in the real and imaginary parts, so u of xy plus I v of xy, and it is defined in some neighborhood of z0, then f is continuous at z0 given as x0 plus iota y0 if and only if u and v are continuous at x0 y0. Now let's see why we need this sentence that this function is defined in some neighborhood of z0. So we also discussed this in our last discussion. So now we want to calculate the limiting value, and we cannot calculate the limiting value at a point if we don't know the behavior or the functional values in some neighborhood of that point. So that's why we require that the function is defined in some neighborhood of z0. Now the proof of this result is very simple. So once again, it is an if and only if statement. So if and only if also means necessary and sufficient condition. So it is basically logical equality between two statements. So the first statement is f is continuous at z0 is equal to iota y0, and the second statement is u and v are continuous at this point x0 y0. And how do we prove this thing? So we first assume that this first statement is true, and then we prove that the second statement is true by some implications, by some middle steps. So in other words, if we assume that this first statement is true, then it should imply that the second is also true. And if the second statement is true, then the first statement should also be true using some simple middle procedures. So that's why assuming that the first statement is true is the same as assuming that the second statement is true. So they are logically equivalent. So how do we prove this thing? We first assume that the first statement is true. The function is continuous at z0 is equal to x0 plus iota y0. And what do we want to show? We want to show that u and v are continuous at x0 y0. So now if the function f is continuous at z0, and remember we have two definitions of continuity at a point z0. So let's use this definition. If the function is continuous at point z0, then the limiting value should be equal to the functional value. Now the function is given as u of xy plus iota v of xy. So this implies that the limit z approaches to z0 of u of xy plus iota v of xy should be equal to f of z0. So this implies limit xy approaches to x0 y0 of u of xy, okay, is equal to the real part of f of z0. Now what is the real part of f of z0? Okay, so real part of f of z0 Now what is the real part of f of z? U of xy. So this is just u of x naught y naught. And similarly, this implies that f limit xy approaches to x naught y naught of this function v of xy should be equal to the imaginary part, because these two sides are equal, so that's why the real parts and imaginary parts must be equal. So the imaginary part of this limiting value is limit z approaches to z naught or limit xy approaches to x naught y naught of v of xy. So it should be equal to the imaginary part of this f of z naught. Now once again, what is f of z? F of z is equal to u of xy plus iota v of xy. And the imaginary part of f of z naught would be v of x naught y naught. So this is equal to v of x naught y naught. So this is the definition of continuity, and then we have the following consequences of this definition. Now recall that a function of two variables is continuous if the following three conditions are satisfied. The limiting value exists, the functional value exists, and both are equal. And we can easily see that in this case, for u of xy, the limiting value is equal to the functional value, and similarly in the case of v of xy, the limiting value is equal to the functional value. So we can say that u of xy is continuous and v of xy is also continuous. Of course, this statement is incomplete, so we need to write down continuous at x naught y naught and at the same point. So this proves the second part, which where we had to show that u and v are continuous at this point x naught y naught. And converse part I am leaving as an exercise. So conversely, I am leaving this as an exercise. So what do we need to prove in the converse part? So in the converse part, we will assume that u and v are continuous at x naught y naught, and then we have to prove that function f is continuous at this point z naught. Now let's see some other consequences of the definition of continuity. So if two functions are given which are continuous at this point z naught, then their sum is another function and it is also continuous at the same point. Okay, so how do we define addition of two functions? It's a very simple procedure. So if a function is given as, let's say, z plus 1, and another function is given as, let's say, z square, then f plus g is another function defined in the following way: f of z plus g of z. Now what is f of z? F of z is z plus 1. And what is g of z? G of z is z square. So basically, this new function, which is the addition of f and g, is this z square plus z plus 1. Now if f and g are continuous, then this result says that their addition, which is another function, is also continuous at the same point. And of course, similarly, we can say the same statement for other operations, for example, difference. So on the same lines, we can also calculate the difference of two functions. And once again, if f and g are continuous at z naught, then the difference f minus g is also continuous at z naught. And on the same lines, we can define the product of two functions. So for example, if f of z is given as z plus 1 and g of z is given as z square, then f into g is another function defined in the following way: f of z into g of z. Now what is f of z? F of z is z plus 1 and g of z is z square. So this becomes z cube plus z square. So this is basically the function f into g, the product fg. So this result says that if f and g are continuous at z naught, then their product is also continuous at the same point z naught. And the last part of this theorem says that if f and g are continuous, then their division, their quotient f over g is also continuous. And of course, we can only say this statement if g of z naught is not equal to 0. Okay. So once again, how do we calculate the quotient? So if f of z is equal to z plus 1 and g of z is equal to z square. Then we can calculate the quotient f over g. It's a function defined as f of z over g of z. And since f of z is z plus 1 and g of z is z square, so this is the quotient of these two functions. And the result says that if f and g are continuous at z0, then this quotient function f over g is also continuous at z0, provided g of z0 is not equal to 0. Now the proof of this theorem is very simple if we use the definition of continuity to be this one. Limit z0, z approaches to z0, f of z is equal to f of z0. And further we can assume that f of z is given as f of x plus iota y, which is equal to u of xy plus iota v of xy. So by taking the real and imaginary parts, and similarly for g of z we can assume that this is equal to x plus iota y is equal to m of xy plus iota n of xy. Now using this definition and using these two descriptions of f and g, we can prove all these statements in a very simple way. And once again, I'm leaving this as an exercise, as a very simple exercise. So what do we have to check? So you have to check that this function f plus g, in the first part, this function f plus g is continuous. In other words, you need to show the following. Okay, so we need to show the following, that the limiting value as z approaches to z0 of f plus g of z is in fact equal to f plus g of z0. And over here you need to use this definition of this addition of function, and using this definition and these two descriptions of f and g, we can easily prove that this statement holds, and similarly the difference, product and quotient continuity can also be proved. Now let's observe some special function. Basically it's a polynomial function, and we want to prove that it is continuous at each point z0 in the complex plane. Now we are going to use this function very oftenly in our later discussions. So by proving that they are continuous, it will give us much more information about this function. Okay, so how do we prove that this polynomial function is continuous? Now observe that this polynomial function has terms separated by this sign of addition. Okay, so the first part is a0, the second part is a1z, and up to so on, and the last part is an zn. Of course it's a polynomial, so this n has to be finite, and all of these powers must be non-negative integers. Okay, so to prove this thing, we will use the previous theorem, where we proved that if two functions are continuous, then their addition is also continuous. Okay, so basically p of z is given as a0 plus a1z up to so on plus an zn. So in the first part we prove that this function is continuous. In the second part we prove that this function is continuous, and then we keep on proving that all these functions are continuous. And then of course if all these functions are continuous, then their addition would also be continuous at point z0. So how do we prove that this function f1 is continuous? So since it is a constant function, a0 is a constant, it's a constant complex number, so all of these coefficients a0, a1, an are basically complex numbers, fixed constant complex numbers. So in this case, if we calculate the limit, then the calculating limit would give us the same number because it's a constant function. So the limiting value is equal to the functional value. So we can say that this function f1 of z, which is just a0, is continuous. So now in the second part we are going to prove that this function f2 Okay, so F2 case, now we want to prove that this F2 is continuous. So how do we prove that? Now we are going to use the epsilon delta definition. Okay, so to show, so what do we need to show? For epsilon greater than 0, there exists delta greater than 0 such that the distance between a1z and the functional value at z0, which is going to be a1z0, is less than epsilon whenever the distance between z and z0 is less than delta, and of course greater than 0. Okay, so how do we find this delta? To apply this definition, so how do we apply this definition? So we assume that this epsilon is arbitrary. Okay, so this is arbitrary. It is any real number that we choose. It is independent of anything. Okay, so it is independent quantity. Now, to prove that this is continuous, what do? So we find this delta, which is basically a function of epsilon. Okay, so the main task is to find this delta. Now let's see how to find this delta. So starting from a1z minus a1z0 less than epsilon. Now we can take common this a1, so it becomes z minus z0 and a1 modulus less than epsilon. So this implies that z minus z0 modulus less than epsilon over a1 modulus. Now this is the observation. Now once again, let's see what do we want to find. Okay, so to find is a delta such that whenever z minus z0 mod is less than delta, then this thing holds. But this thing is logically equivalent to this statement. So this gives us the idea that if we take delta to be epsilon over the modulus of a1, then this implies that this quantity will be less than epsilon. In other words, so taking delta to be epsilon over modulus of a1 implies that f2 of z minus f2 of z0 is less than epsilon whenever z minus z0 is less than epsilon over modulus of a, and of course this is greater than 0. So we have found this delta, so that's why we can say that this function a1z is continuous at z0, and z0 is an arbitrary point. So far we have proved that this a0 is continuous, a1z is continuous. Now on the same lines and using previous properties of complex valued functions and their continuity, we can prove that this function f3 of z, which is equal to a2 z square, is continuous. So why it is continuous? Because it is product of three functions, you can say. So first function is this continuous constant function a2, and then we have z, and then we have z. And we have proved that this z is continuous, and a2 is continuous, and the product of continuous is continuous. So this implies that f3 is continuous. And continuing in this way, we can prove that all these terms of this polynomial are continuous functions. And of course, it's continuous at z0. And now using the property that if f and g are continuous at z is equal to z0, then f plus g is continuous at z0. So using this property, we can say that all the terms are continuous and their addition is also continuous. So this implies this polynomial function, which is the sum of all these continuous functions, is also continuous. So this polynomial is continuous at z is equal to z0. And z0 is arbitrary point of the complex plane, so that's why we can say that a polynomial function is always continuous function. Now we can use the continuity of polynomial to calculate some limits as well. So what kind of limits? So the limits which are, for example, limits of rational functions. Okay. So once again, we are going to use property of continuous functions. So what property we are going to use here? So if f and g are continuous, at z0, then the quotient f over g is continuous at z0, provided, of course, g of z0 is not equal to 0. So this numerator z squared plus 2 is basically a polynomial which is continuous according to our previous proof, and the denominator is also a polynomial which is continuous once again using our previous result. And so the quotient of these two polynomials is continuous at point wherever the denominator is not 0. Okay, so we can see that if we put z is equal to iota in the denominator, then the denominator is not equal to 0. So we can say that the limiting value as z approaches to iota is equal to the functional value, since this is a continuous function at point z is equal to iota. So the value become iota square plus 2 divided by iota square minus 2 iota plus 1. So basically 2 minus 1 over minus 1 minus 2 iota plus 1. So this becomes 1 over minus 2 iota. So that's how we can calculate some limits using the property of continuity of complex valued functions. So in this discussion, we saw some consequences of the continuity property of complex valued functions. In our further discussion, in our next part, we are going to continue this discussion and we will see some further consequences of the continuity of complex valued functions.